You know when you see those incredible videos from inside a factory and you just wonder, how does a robot actually see what it's doing? Well, today, we're going to pull back the curtain and take a journey deep inside the amazing world of robot vision.
I mean, it seriously looks like magic, doesn't it? A robot arm flawlessly plucking one specific part from a conveyor belt that's constantly moving. But here's the thing, it's not magic at all. It's actually a super sophisticated process of seeing, then thinking, and then, finally, acting.
And this diagram right here, well, that's going to be our roadmap for this whole explainer. We're going to follow this flow step by step, all the way from how the robot first lays its eyes on an object to the final command that makes its arms spring into action.
So, let's dive in with the very first, and maybe the biggest challenge of all, sight itself. You know, it's one thing for a camera to just snap a picture, but it is a whole other ballgame for a machine to perceive the world in a way it can actually understand and use.
When you boil it all down, this whole process is really a series of translations. It all starts with the physical world, with light itself. That light gets converted into digital data, and then that data gets translated one last time into a very precise physical movement. Light to data to action. All right, so let's break that down, starting at the very beginning. How in the world does a robot even capture a good, clean image of what's in front of it?
Now, here's something that might surprise you. A robot's vision doesn't really start with the camera, it starts with the light. Getting the illumination just right is absolutely critical. For example, if you need to measure an object's exact size, you'd probably use backlighting to get a perfect, crisp silhouette. But if you're looking for tiny little scratches on a surface, you'd hit it with some side lighting to make those defects really pop. It's all about choosing the right tool for the job.
So you can see that sequence right here. First up, the illumination system bathes the object in just the right kind of light. Then the camera, which is kind of like the one in your phone, just more specialized, captures all that reflected light and turns it into a raw electrical signal. And finally, a piece of hardware called a digitizer steps in and translates that signal into a digital image that a computer can actually read.
And this gives you a great visual of that whole conversion. You see that smooth, analog wave? That's the light the camera sees. The system takes little measurements or samples of that wave at thousands of points. Each one of those little samples gets a number. That's called quantitation. And then the whole thing gets encoded into binary. And just like that, a physical wave of light becomes a simple digital string of ones and zeros. Pretty cool, right? Okay, so the robot now has a digital picture, but a picture is just a giant grid of pixels. Now comes the really hard part, the brain work. How to find actual meaning in that sea of data.
The very first job is to clean up the scene. This is a process called segmentation. The easiest way to think about it is like the robot is digitally cutting out the objects it cares about from everything else. It separates the bolt from the conveyor belt, basically telling the computer, hey, pay attention to this part, everything else is just background noise.
All right, now that the object is all by itself, the system does something called feature extraction. It's not looking at the whole bolt anymore. Instead, it's acting like a detective, looking for clues, its key characteristics. What's its exact shape? How many corners does it have? What are its precise dimensions? It's gathering all the evidence it needs for the big reveal. And this is the aha moment. This is object recognition. The system takes all those features it just collected, all those clues, and it compares them against a huge library of objects it already knows about. When it finds a match, it's a double win. It doesn't just know what the object is, it also knows its exact position and rotation on that belt. So, think about where we've been. We've gone from light to pixels, and from pixels to actually identifying an object. But we can't forget the whole point of all this. All of this intense digital analysis has one single goal: making a precise, physical action happen in the real world.
And that's where the robot controller comes in. It's the final piece of the puzzle, the true brain of the operation. It takes all that what and where information from the vision system and translates it into the exact motion commands for the robot arm. And I just love how this flowchart shows that final step so perfectly. I mean, all of that incredibly complicated vision processing we just talked about, it all comes down to this super simple, clear set of instructions. Move to this spot, close the gripper. Move to that spot, open the gripper. That is it. In that one moment, seeing has officially become doing. But, of course, none of this just happens on its own. A robot only knows what to look for because a person taught it. And that brings us to a really important part of the story, the human in the loop, aka the programmer.
And there are really two main ways to do this.
There's online programming, which is kind of like teaching the robot right there on the job. It's quick for simple stuff, but you have to stop the whole production line to do it. Then there's offline programming. That's more like doing homework. You build and test these really complex programs in a computer simulation without ever stopping the real robot. It's way more efficient for the complicated jobs. And the languages we use to even talk to these robots have totally transformed over time. We started with what are called first-generation languages, which were really just about defining simple movements from point A to point B. Then we got second-generation languages, which were much smarter and could use data from sensors, like a vision system. And now? Well, now we're rocketing towards the future. AI-based systems where you don't even program how to do something. You just tell the robot the goal, and it figures out the best way to get it done all by itself.
So after all that, where does this technology actually take us? Well, it takes us to a world that is being fundamentally transformed by machines that can see.
And honestly, the applications are everywhere in modern industry. You see it in basic pick-and-place tasks, sure, but also in unbelievably precise quality control, spotting flaws that are totally invisible to the human eye. We see it assembling our delicate electronics, tracking seams for perfect welds, and tackling one of the hardest challenges out there, using 3D vision to pick one specific part out of a chaotic, jumbled bin of other parts.
This quote from the source material really just nails the whole thing, doesn't it? Robot vision enables the robot to see, understand, and interact intelligently with its environment. It's that complete package, from sight to understanding to intelligent action, that makes this all so powerful. Which leaves us with one last, really fascinating question to think about. So far we've mostly taught robots to see things like car parts and circuit boards. But as this technology keeps getting better and better, as it becomes more powerful and more intelligent, what on earth will we teach them to see next?